Welcome back to the Deep Dive. Today we are strapping in for uh, a deep dive into two truly revolutionary concepts happening right now, right at the very edge of physics, material science, and computation. And we're not talking about small improvements here. We're talking about sources that fundamentally change how we engineer matter and light at the quantum level.
To create devices and, computing platforms that were literally thought impossible just a few years ago.
Exactly.
That's right. Our mission today is to give you a shortcut to understanding these breakthroughs. We have two distinct, very high-impact discoveries. First, we're looking at ultra-efficient next-gen electronics. Scientists have engineered a microscopic sort of traffic light for charge carriers.
Traffic light.
Yeah, controlling these fundamental particles called chiral fermions using nothing but the internal geometry of a crystal. No magnets required.
Which is a huge deal. And second, we're going to pivot to computing architecture. We'll be unpacking entropy computing, which is a brand new paradigm that harnesses light and, well, fundamental randomness entropy to solve the world's hardest computational challenges.
The notorious NP-hard optimization problems.
The ones that bog everything down.
Right. And it does it faster and cleaner than specialized classical machines. Our mission is to extract the most shocking discoveries from both of these papers, give you the distilled knowledge.
So you can walk away knowing exactly why these breakthroughs are setting the stage for the next decade of technology. So let's start small, down at the particle level. Because this first deep dive, it really does feel like science fiction.
It does.
When we talk about next-generation electronics, the main challenge is finding low-power, efficient ways to control charge carriers, like electrons.
Of course.
Electrons carry charge, we all know that. But in certain exotic materials, these topological materials, they also have a very subtle property called chirality.
A kind of inherent handedness. Think of it like a microscopic screw threading through the material.
Aye.
A left-handed fermion is spinning or moving one way, and a right-handed one is moving the opposite way.
And harnessing that chiral degree of freedom is essential for creating powerful, low-power topological electronics.
It is.
But traditionally, if you wanted to separate or control these left chiral and right chiral fermions, you needed to apply these massive external magnetic fields.
Right, or you had to introduce magnetic dopants into the material. Both of those options are complex, they're bulky, and they just consume too much energy.
So the fundamental question the researchers were asking was, how do you filter particles based on their handedness without a huge, power-hungry magnet?
And the answer they found is startlingly elegant. You leverage the material's internal quantum geometry.
Quantum geometry. Okay, let's unpack that. The material they used was single crystal palladium gallium, or PdGa. What does quantum geometry even look like in this crystal, and how does it act as a filter?
Well, the geometry refers to the inherent crystallographic structure, the really precise, specific way the atoms are arranged.
I see.
In PdGa, this structure naturally gives rise to electronic chirality. But the key insight is that the internal shape of the crystal lattice itself contains this hidden force. It's composed of two topological components, the Berry curvature tensor and the quantum metric.
So when they apply an electric current, this internal geometry, this Berry curvature, it generates what I call an anomalous velocity in the chiral fermions. So it's not simply pushing the particle forward, it's an internal invisible force that pushes particles sideways based on their quantum handedness.
Precisely. They're exploiting the nonlinear Hall effect, the NLH. This effect means that when they push current straight through the main channel of the material, the material's geometry itself pushes different particles sideways into different output channels. It's the ultimate microscopic traffic sorter.
And this is where the device geometry comes in. They built a three-arm device, a central lane splitting into a left arm and a right arm.
And the sources detail this just shocking separation they achieved.
What do they see?
A really clean separation of different topological states. The left chiral fermions, which occupy what's called the A Fermi pocket, they have a specific quantum label, a Chern number of -4.
Okay, C equals -4.
And they scatter preferentially into the right arm. Meanwhile, the right chiral fermions from the opposing R Fermi pocket with a Chern number of +4,
they go the other way.
They scatter into the left arm.
So the Chern number is basically the quantum label telling the particle which traffic lane to take.
That's a great analogy. And crucially, the ordinary non-topological electrons, the trivial traffic, they scatter primarily into the middle arm.
Wow.
They successfully filtered the topologically protected charge carriers from the trivial ones in a single device, and all without a magnetic field.
This chiral fermionic valve, as they call it, it has huge implications. So it separates the fermions, but the separation does two other remarkable things. First, it enables tunable, current-induced orbital magnetization.
That's fascinating. It means the separated currents are actually carrying their own magnetic momentum.
So the current in the left arm
Carries an orbital magnetic polarity opposite to the current in the right arm. They've effectively created a current-controlled magnetic dipole just by separating handedness.
and the second thing,
It provides a platform for controlling quantum interference of these quasi-particles.
which leads us to the most convincing proof that this effect is truly quantum, not just some weird classical scattering.
Absolutely. The evidence is twofold. First, the NLH response, that critical sorting action, it only appears above a specific threshold current,
What was it?
around 55 microamps. This is key. It's like flipping a quantum switch. Below that energy level, it acts like an ordinary material.
But cross that threshold?
And the quantum geometry wakes up and starts sorting the particles.
A quantum tipping point. And then there's the long-range coherence proof. They built a Mach-Zehnder interferometer, an MZI, in the material, and they saw quantum interference of these separated chiral currents flowing through the two arms over a distance of more than 15 micrometers.
And in the world of quantum electronics, 15 micrometers is an extremely long distance for a coherent phase effect to survive.
That's incredible.
It speaks volumes about the robustness, the topological protection of these charge carriers. They aren't easily scattered or disrupted.
And they established two major ways to control this valve. First, the passive control.
Right.
By simply changing the crystallographic orientation, the angle they apply the current at, they could switch the device between valve on, IR on, and so on.
And then the exciting step toward active control. They integrated a magnetic tunnel junction, an MTJ, onto one of the device arms.
So they could tune it on demand.
Exactly. By influencing the orbital magnetization of that arm, they showed they could actively tune the valve state.
This magnetic field-free method for controlling chirality. It's a clean path toward next-gen, ultra-low power topological electronics. It's just incredible control at the very foundation of hardware. Now, let's pivot from controlling single particles to solving global computational bottlenecks.
A big jump.
A big jump. Our second deep dive is into entropy computing. The problem here is NP-hard optimization logistics, complex scheduling, drug design, max cut problems, all the challenges that bog down traditional computers.
NP-hard problems are the world's computational pain points. And if you try to use one of the existing specialized solvers, like, the popular Ising machines, you hit a fundamental limitation.
Which is?
They are built to deal only with binary states, zeros and ones.
Which means if your real-world problem involves continuous numbers or, multiple integer options, you have to use these complex mathematical tricks.
Like quadrization.
Right, just to make it fit the hardware.
Exactly. You add tremendous mathematical overhead, auxiliary variables, all this complexity just to frame the problem. Entropy computing completely bypasses that.
How does it work?
It uses an open photonic system driven by rapid measurement and feedback to continuously search for the optimal solution. It does this by promoting the stabilization of the ground state.
The minimum energy or minimum entropy state of the system.
That's the one.
Okay, let's talk hardware. They demonstrated this with a system called Dirac-3. It's a hybrid system, part light, part electronics.
That's right. The system uses temporal photonic modes, or time bins, to encode variables as qudits.
A generalization of qubits.
Right. They can hold more than just two values. And a weak coherent state of light loops through 4 key components. You have an electro-optical modulator, an EOM that encodes the data, a single photon detector, or SPD, that's important, and then an FPGA.
A field-programmable gate array.
Which calculates the loss function and provides instant feedback to the light modulator.
So structurally, what makes this so much better than the specialized Ising solvers? Beyond avoiding the whole binary limitation, what are the core advantages?
The advantages are immense, and it's primarily because of the objective function it minimizes.
Okay.
Since it's not limited to the Ising model, Dirac-3 naturally handles continuous and integer variables. But the critical difference is in the polynomial cost function, ADO.
And this is where it gets really interesting.
Absolutely. While traditional specialized hardware is limited to quadratic interactions, 2 variables at a time, the Dirac-3 system's cost function can incorporate high-order interaction terms.
How high?
Up to the 5th order.
Wait, 5th order? That's PIEV, JVK, VE, VL, VMR. I mean, traditional solvers force you to reduce every problem down to an interaction between just two variables at a time.
Right.
This fifth-order capability must dramatically simplify encoding these huge chaotic problems.
It doesn't just reduce complexity. It means they can model problems that look like a sprawling, chaotic city network without having to, build a million auxiliary roads just to force the map onto a simple grid.
It naturally allows for dense, long-range interactions.
Which is essential for modeling complex networks in the real world.
This sounds almost too clean. How does the system avoid getting stuck in suboptimal local solutions? That's the Achilles heel of classical optimization.
That is where the entropy part, or the controlled fluctuation, comes in. Since the system relies on detecting weak coherent states of light, it intrinsically uses the shot noise from single photon counting as its primary source of randomness.
So the randomness that's just inherent in counting tiny numbers of photons, that acts as the escape mechanism.
It does. This stochastic element allows the system to behave in a quantum tunneling-like way. It gives it the ability to hop out of local minima and search the solution space much more effectively.
And the counterintuitive finding was that more noise equals better performance.
Right.
They found the best solutions when operating in an ultra-low mean photon number regime between a 0.03% and 1.33% probability of single photon.
That's right. The more the system relied on that fundamental fluctuation, the better the solution quality became. It promoted a global search.
And this is backed up by some serious benchmarks.
Very serious. For a non-convex quadratic problem, QPLIB 00888 with 50 variables, Dirac-3 found the global ground state in almost 80% of runs.
That's highly significant. Conventional gradient descent algorithms, which are the workhorse of optimization, they get stuck in local minima constantly.
All the time.
Finding the guaranteed global optimum 80% of the time, especially with non-convex problems, is a massive leap in quality.
And then for the notoriously difficult NP-hard problem, max cut, the Dirac-3 system provided superior solution quality to standard semi-definite programming, or SDP relaxation methods on a 30-node graph.
And SDP is often used as the baseline for hard optimization, so outperforming it is a big deal.
It speaks volumes about the power of this architecture.
And all of this is achieved using a system that consumes less than 100 watts of power.
In its current hybrid form, yes, incredibly low energy consumption, with the promise of even greater efficiency if they move to a full all-optical implementation.
So it addresses both the scale and the difficulty of the world's hardest problems at the same time. So let's synthesize these two dives. In the world of quantum materials, the PdGa valve gives us this unprecedented control over particle flow at the subatomic scale. It offers a clean, low-power switch that leverages geometric effects. We learned how to manipulate particles just based on their fundamental handedness.
And in the realm of computation, entropy computing gives us a powerful new conceptual tool to solve complex, real-world optimization problems. It fundamentally changes the architecture by leveraging controlled fluctuation and these high-order cost functions.
And both are driven by physicists engineering and exploiting these non-trivial quantum effects geometry in one case.
And the quantum fluctuation in the other.
So what you've gained today is insight into two of the most exciting frontiers in physics. Controlling elementary charge carriers for dramatically better hardware and fundamentally changing the architecture of optimization.
And this isn't just about making faster chips. This suggests a future where device complexity is less about raw size and more about harnessing the exotic, subtle behavior of quantum materials. And this new knowledge hints at a potential convergence point. We learned that the chiral currents flowing through that PdGa valve carry orbital magnetization,
creating a tiny current-induced magnetic moment that's highly tunable.
Exactly. Meanwhile, entropy computing uses rapid, controlled fluctuation and feedback loops to find optimal solutions.
So here's a final provocative thought for you to chew on. If that PdGa valve provides a clean, fast, current-induced way to create and manipulate these internal magnetic moments using quantum geometry, and the next generation of entropy computing requires high-speed, precise control inputs for its optimization loops, could that quantum geometric switch be used as the active control knob or dissipative element in a future all-optical entropy computer? The ultimate goal isn't just better switches or better computers. It's merging the quantum geometric switch directly into the quantum computation engine. Think about that convergence. We'll see you next time on The Deep Dive.